Hello students, welcome back. In this chapter, we're going to discuss estimation and confidence intervals. So our focus of study begins with a point estimate, a single value, and interval estimates, a range of values, and we also learn a method to determine the necessary sample size. So there are 5 learning objectives. The first one is to compute and interpret a point estimate of a population mean. Second is to compute and interpret a confidence interval for a population mean. Third is to compute and interpret confidence interval for a population proportion. Fourth, calculate the required sample size to estimate a population proportion or population mean. And fifth, to adjust a confidence interval for finite populations. So let's start with a point estimate. So basically a point estimate is a single value or statistic used to estimate a population value parameter. Okay. So, for example, the Bureau of Tourism of Barbados wants an estimate of the mean amount spent by tourists visiting the country. They randomly select 500 tourists as they depart and ask these tourists about their spending while there. The mean amount spent by a sample of 500 tourists serves as an estimate of the unknown population parameter. Okay, so basically, since it's not feasible to contact all visitors visiting Barbados, so we can rely on sample information. The second one is confidence interval. So basically, it's a range of values within which the population parameter is expected to occur. So the definition itself is a range of values constructed from sample data so that the population parameter is likely to occur within that range of specified probability. The specified probability is also called the level of confidence. Okay, so basically there are two situations for computing a confidence interval for a population mean. So one situation is when the population standard deviation is known, and the second situation is when the population standard deviation is unknown. So there are 3 factors that determine the width of a confidence interval. The first one is the number of observation in the sample n. Second is the variability in the population, usually estimated by the sample standard deviation s. And third is the desired level of confidence, 95%, 99%, for example. Okay, so let's start with level of confidence when the standard deviation of the population is known. To determine the confidence limits when the population standard deviation is known, we're going to use the z distribution. So basically the formula is the following: x bar, which is the sample mean, plus minus z times sigma divided by the square root of n. Okay, so basically we know the population standard deviation when we have a long history of collected data. Okay, so knowing the population standard deviation allow us to use the standard normal distribution. Okay, so let's discuss on how to find a value of z. So basically, the method for finding z for a 95 confidence interval is the following. First, we're going to divide the interval in half. So basically, 95% is 0.95 divided by 2 is 0.4750. Find the value 0.750 in the body of the table. Now we're going to identify the row and column and add the values. And the probability of finding a value between 0 and 1.96 is 0.750. So basically the probability of finding a value between plus minus 1.96 is 0.95 or 95%. The steps are the same for a 90% confidence interval. So in fact, we can select any value between 0 and 100% and find the corresponding z value. Okay, so we can use the standard number table, which you can find in the Appendix B in the book or in the internet. Okay, so let's take an example. The American Management Association, AMA, is studying the income of store managers in the retail industry. A random sample of 49 managers reveal a sample mean of $45,420, and the standard deviation of the population is $2,050. what is the population mean, and second, what is the reasonable range of values for the population mean, and how do we interpret the result. Okay. So basically in this example, we're going to use the sample mean to construct the confidence interval results in endpoints. Okay, so let's calculate the endpoints. But first, let's answer whether what's the population mean. Well, we don't know the population mean. We can use the sample mean of 45,420 as our best estimate. So let's use 95% level of confidence, and so basically Z is going to be so what we can do is we can actually calculate $45,420 plus minus 1.96 multiplied by the standard deviation of 2050 divided by the square root of 49. So basically it's going to be 45,420 plus minus 574. So the endpoints or the confidence interval is from 44,846 to 45,994. So these are the endpoints. So basically $574 or Z multiplied by sigma divided by square root of n is called the margin of error. Okay, so to extend the interpretation of these results, now suppose that we select many samples of 49 store managers, perhaps several hundred. For each sample, we compute the mean of the sample and construct a 95% confidence interval. We could expect about 95% of these intervals to contain the population mean. Okay, and about 5% of the intervals would not contain the population mean. This is due to the sampling error, and the risk is we assume that we select the this is due to sampling error, and it's the risk we assume when we select the level of confidence. So what happens in the calculation of the confidence interval if sigma is unknown? Well, if sigma is unknown, we can use what's called the t distribution. Okay, so in most sampling situations, the population standard deviation is not known, and so since we don't know, we can use what's called the sample standard deviation S instead of sigma as an estimate of sigma. Okay, now instead of using the Z distribution, we're going to use the T distribution. So for example, here the dean of the business college wants to estimate the mean number of hours full-time students work at paying jobs each week. He randomly selects a sample of 30 students and asks them how many hours they worked last week. So he can calculate the sample mean, but it's unlikely he would know the population standard deviation required for formula 9.1. So again, if we can assume that the population is normal and the standard deviation is known, we can always use the Z distribution. And if we assume that the population is normal, but the population standard deviation is not known, we're going to use the T distribution. Okay. So what are the characteristics of the T distribution? The T distribution is a continuous distribution. It's mound-shaped and symmetrical. It is flatter or more spread out than the standard normal distribution, and there is a family of T distributions depending on the number of degrees of freedom. So let's find a value of T. So again, we're going to first assume that the population is normal. We can use table T in Appendix B.5. So what we're going to do is we move across the columns identified for confidence intervals. So in the next example, we want to use the 95% confidence. So let's move to the 95% column. The next thing that we're going to do is find the degrees of freedom, and the degrees of freedom is n minus 1, or the total sample minus 1. Okay, so basically when sample statistics are being used, it's necessary to determine the number of values that are free to vary. So basically the degrees of freedom is found by taking the sample size minus 1. That's going to be the common way of finding it. Okay, So let's take a look of the method to calculate level of confidence using the T. Okay, so a tire manufacturer wishes to investigate the tread life of its tires. A sample of 10 tires driven 50,000 miles revealed a sample mean of 0.32 inch of tread remaining with a standard deviation of 0.09 inch. Construct a 95% confidence interval for the population mean. So will it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.30 inch? So basically, we have a sample mean of 50,000, and we have a sample mean of 0.32 inch, and we have a sample size of 10, and sample standard deviation of 0.09. So basically, let's construct the 95% confidence interval. So we have 0.32 plus minus 2.262 times 0.09 divided by the square root of 10. So basically we have 0.32 plus minus 0.064. So the endpoints of the confidence interval are 0.256 and 0.384, and the margin of error is 0.064. So the manufacturer can be reasonably sure with 95% confident that the mean remaining thread depth is between 0.256 and 0.384. Because the value of 0.30 is in the interval, it's possible that the mean of the population is 0.30. Okay? So I'm gonna provide you with an alternative interpretation of the 95% confidence interval. Now suppose that we repeat the study 200 times and calculating the 95% confidence interval with each sample's mean and standard deviation. We can expect 190 of the intervals would include the population mean. Okay. Okay. So the next step is the confidence intervals for proportion. So proportion, the fraction, ratio, or percent indicating the part of the sample or the population having a particular trait of interest. A sample proportion P is found by X, the number of successes, divided by N, the number of observations. So for example, Southern Tech Career Services reports that 80% of its graduates entered the job market in a position related to their field of study. A recent study of married men between the ages of 35 and 50 found that 63% felt that both partners should earn a living. So basically, in this earlier example, we use ratio scale of measurement. Now in this section, we use the nominal scale of measurement since the outcomes will be limited to two values, 0 or 1. In the Southern Tech example, a graduate either entered the job market in a position related to his or her field of study or not. Married men either felt that both partners should earn a living or they did not feel that way. In each example, an observation is classified into one of the two mutually exclusive groups. We can refer the two groups in terms of proportions. Okay, so a population proportion is going to be identified by pi, and there are two requirements. The first one is that the binomial conditions have been met. So we can look at the binomial conditions in the previous chapter, particularly chapter 6. One, the sample data are the number of successes in n trials, and there are only two possible outcomes, success or failure. Third, the probability of success remains the same from one trial to the other. And fourth, the trials are independent. Okay. Now the values n times pi and n minus 1 times pi should be greater than or equal to 5. So the second requirement allows us to invoke the central limit theorem and employ the standard normal distribution and use z to complete a confidence interval. So the confidence interval for a population proportion is just p plus minus z multiplied by the square root of p times 1 minus p divided by n. So basically p times 1 minus p square root is just the standard deviation and divided by the square root of n. Okay, So let's take an example. The union representing the Bottles Blowers of America, BBA, is considering a proposal to merge with Teamsters Union. At least 3/4 of the BBA membership must approve any merger. A random sample of 2,000 current members reveal 1,600 plan to vote for the merger proposal. What is the estimate of the population proportion? Can you conclude that the necessary proportion of BBA members favor the merge, and why? Okay, so basically there is a random sample of 2,000. So basically n is 2,000 and 1,600 plan to vote for the merger proposal. So basically the sample proportion is going to be 600 divided by 2,000, which is 0.80. Okay, and let's use the previous formula to determine the 95% confidence interval. So basically it's going to be p plus minus z multiplied by square root of p 1 minus p divided by n. Okay, so it's 0.80 plus minus z, which is about 1.96, multiplied by 0.80 multiplied by 0.20 divided by 2,000, and then take a square root of that. So the endpoints that you'll get is 0.782 and 0.818. So we can conclude that the merger will likely pass because the interval estimates include values greater than 75% of the unionship membership. Okay. Next up is a discussion on determining sample size for means. So basically there are three factors that determine the sample size when we wish to estimate the mean. The first one is the margin of error. The second one is the desired level of confidence, for example 95%. Third is the variation in the population. So basically the formula for the sample size is n equal to the square of z multiplied by sigma divided by e. Okay, so the result is not always a whole number, so what we can do is just round up the fractional result to the next whole number. Okay, so we can choose relatively high levels of confidence such as 95% and 99%, and we use z statistics. Okay, now what happens if the population standard deviation is not known? Well, what you can do is you can decide to conduct a pilot study, you can use a comparable study, or you can use a range-based approach to find this value. Okay. All right. So let's take an example. A student in public administration wants to estimate the mean monthly earnings of city council members in large cities. She can tolerate a margin of error of $100 in estimating the mean. So basically E is $100. She would also prefer to report the interval estimate with a 95% level of confidence. So basically the Z is going to be 1.96. And the student found a report by the Department of Labor that the standard deviation of $1,000. So basically N is going to be Z multiplied by sigma divided by the margin of error and to the power of 2. So basically it's going to be 1.96 multiplied by 1,000 divided by 100 and take a square root of, take a power to the power of 2. So the computed value is 384.16, and then we can round it up to 385. So basically a sample size of 385 is going to be required to meet the specifications. Okay. Now, what happens if the student wishes to increase the level of confidence, for example 99%? Well, we're going to need a larger sample. So instead of multiplying with z equals to 196, we're going to multiply it by z equals to about 2.56. Okay. So in this particular case, we're going to need about 664 samples. So larger samples will increase the cost of the study, so the level of confidence should be considered carefully. Okay. Now, what about the sample size if we talk about proportions? Well, basically, in this particular case, we're not going to be able to have what's called the standard deviation. And so we need to calculate the standard deviation using the pi, okay, which is the population mean. So basically, we need to understand the margin of error, the desired level of confidence, and the value for pi to calculate the variation in the population. So it's going to be n equal to pi 1 minus pi multiplied by z over e to the power of 2. Okay, so if a reliable value for pi cannot be determined with a pilot study or found with a comparable study, then a value of 0.50 can be used for pi. Okay, why? Because this results in largest possible value and will overstate the sample size. So basically here you're going to a conservative mode. Okay, so using a larger sample size will never hurt the estimation of the population proportion. Okay, so the student in the previous example also wants to estimate the proportion of cities that have private reviews collectors. So the student wants to estimate the population proportion with a margin error of 0.10. So E is going to be 0.10, and they prefer a level of confidence of 90% and has no estimate for the population proportion. So basically, what's the required sample size? So in this particular case, Z is going to be about 1.645 or 1.65, and then we can use pi 0.50. So we can use 0.50 because it's going to give you the highest or the largest possible sample, and E is going to be 0.10. So the formula is going to be 0.5 multiplied by 0.5 multiplied by 1.65 divided by E, which is divided by E of 0.10 and to the power of 2. So basically you're going to get 67.65, and so the total number of sample is 68 cities. So the last discussion for this chapter is finite population adjustment. So a population that has a fixed upper bound is finite. So for a finite population, the standard error can be adjusted by what's called the finite population correction factor, square root of n minus n divided by n minus 1. This will make your estimate more precise by reducing the standard error and resulting in a smaller range of values in estimating the population mean. Okay, so finite population can be small, like all the students in your statistics class, or it can vary very large, such as all senior citizens living in Florida. Okay, so let's start. So basically in this example, there are 250 families residing in Scandia, Pennsylvania. A random sample of 40 of these families revealed that the mean annual church contribution was $450 and the standard deviation was $75. What is the population mean? What is the best estimate of the population mean? Well, basically we don't know the population mean, so the best estimate is the sample mean of $450. And let's develop a 90% confidence interval for the population mean. So basically what we know is the sample mean of 450 and sample standard deviation of $75 and sample size of 40. And basically the formula is going to be sample mean x bar plus minus t multiplied by the sample standard deviation divided by the square root of 40. So basically we're going to have $450 multiplied by 1.685 multiplied by $75 divided by the square root of 40. So we're going to get $450 plus minus 18.35. So the endpoints are going to be 431.65 and 468.35. So the population mean could be 445. It is not like the population mean 425, since 425 is not within the confidence interval. Okay. Now, in this particular case, the population is finite. So again, there is a limit to the number of people residing in Scandia. So we don't know the population standard deviation, so we'll just use the t distribution. So, if you drop to degrees of freedom rho 39, the t value is 1.685. That's why we use t equals to 1.685 in this particular example. Okay, so thank you, and I'll see you guys in the next chapter. Bye-bye.